So in this case, we are going to have a continuation, still working on the brakes. And now these are block. What we have here is what are block brakes. So the block brakes, they are actually, when you consider a block brake, it consists of a block, right? So it actually consists of a, a block. It consists of a block which is made of what? Made of wood. So it is made of wood or similar materials that is lined with a frictional or a friction material. So we are saying we can have any similar materials that is lined with what? A friction material. So that is what you have as the block breaks, which is here. We are given as a block break is a shoe made of what? Wood or metal with the friction material. So in other textbook, they can say or similar materials. All right. Here or metal with friction material on the what? On the contact surface. So a block is pressed onto the rotating brake drum by a perpendicular force at the end of the actuating lever, which is pivoted to a fixed fulcrum. So this is the case that you're going to see later on. So here, that is the statement that the block is mounted on an actuating lever on a pivot. That is what the block is being pressed onto the rotating brake, on the rotating brake drum by a perpendicular force at the end of the actuating lever, which is pivoted to a fixed what? Fulcrum. So that will be pivoted to a fixed fulcrum. So that's what we can have on that statement in expansion. So when a force is applied to the lever, the block is pushed against the drum, then the shoe is either attached on an actuating lever or mounted on what? On hangers. So an actuating lever is simply a device used to what? To bring a part or assembly into operation. That's an actuating what? An actuating lever. So I'm going to show you guys later on the positions on how to have your calculations in terms of the way that the frictional force is going to be presented. So there are two types that we can use or that we can play around when dealing with what? Our block breaks. The single block or a double block. So you've got a single block break or a double block break. The contact surface of the shoe of the block brake is curved to the shape of the drum surface when the shoe comes into contact with the what? With the surface of the drum. Then three assumptions can be made. And these are the basic assumptions that we are going to need for calculations. All right, for calculations. We are going to assume that the resultant normal force of the brake hanger on the shoes passes through the center line of what? Of the shoe. It passes through the center to say the resultant normal force, which is the reaction on the shoe acts, it actually acts radially. It acts radially through the what? Through the center. Through the center of the shoe. So this is the part that we are referring to. It acts radially through the center of what? Through the center of the shoe. So it's an assumption to be made. Also assume that the resultant friction, all right, which is the product of the coefficient of friction to our normal force, that our R there, is a point of application at the center of what? At the center of the shoe. And at a radius R from the center of the drum. And at a radius from the center of the drum. So in actual sense, we are saying that the resultant friction force acts at a center of the shoe and its line of action is tangential to the drum, because we are saying that to be having the drum also considered. So we are simply saying its line of what? Of action is tangential to the drum. All right, we're gonna look into that one, which is very, very important. Then also the other thing that you must consider is that, all right, here it is a separate point which is being given. All right, the resultant and its line of action tangential to the drum, okay, which is okay. Then also, if we are to consider the contact angle of the shoe is less than 60 degrees, so that the normal pressure is what? Is uniform. So you are going to have also the contact angle. Remember, our contact angle is called what? Is called theta. So the contact angle of what? Of the shoe is less than 60 degrees. So that the normal pressure is uniform. The normal pressure is what? Is uniform. So it's another point also that we are to consider when we are working with this, and there are ways that we are going to have in connection. So I want you to go through, according to your textbook, go through the single block, the notes that are important, and also the double block break, all right, and the diagrams. It's very, very important for you to note that. So this is what I want us to consider as the cases or ways in which the fulcrum can be positioned. The ways that we can have the fulcrum what? Positioned. Number one, we can have the line of action if the line of action of the tangential force, which is our tangential friction force, passes through the fulcrum. It passes through our fixed point. We have the point here, or which is gonna be our fulcrum, all right? So if we check according to the anti-clockwise direction, the line of action of the tangential force, or which is this part is given as a tangent, will be straight. It passes through the what? The fulcrum. It passes through. It can be on a clockwise rotation where our frictional force is going to be presented that side as a tangent in the direction that we have. So it's continuous. This is anti-clockwise. We're going to have it in that same direction as we have it. All right. So it is still passing through because this is our fulcrum. So if we take this straight, it must pass through that. When that conditions happened, we can use the moments to calculate whatever that we want using this condition. But for the sake of revision and whatever that you're going to have later on, you can use A as it is here, but I just want us to use S. And all right, so I'm just gonna change this A and B, guys. As for me, I'm just gonna change A and B. Sorry for that. But you can use those A and B. It's fine. What I'm doing here is that is for the formulas that you're going to have before, so that you properly understand what exactly that A represents, what that B represents. So it's not a problem. You can maintain that A and B, or you can use this one S as the distance from the pivot point to the force. So the distance from the pivot point, all right, from our pivot point, the distance to the what? To the force that we have at the end. Whatever part that force will be at, the distance from the pivot point to the force is going to be S. And the distance from the pivot point to our normal force, which is Fn. So remember last time there we had the use of R. So guys, Fn as your normal force, one and the same. Do not worry for that one. So you can maintain the Fn. So it depends textbook, but we can just maintain Fn. So that distance from the pivot to our Fn, the normal force, is going to be L. So we're going to use L there. All right. So that is it. We are going to apply this. All right. So it's the same thing here. This will be our S from the pivot to the force, from the pivot to Fn is going to be L. So there are two, as we can see, one for anti-clockwise, the other one for a clockwise. So you take your moments about the fulcrum, about the pivot point. So taking our moments about this, we're going to consider some of anti-clockwise, some of clockwise moments, depending with what you have. So in our case here, this, as we consider F going this side to the fulcrum, is going to be, this is clockwise. So these are clockwise, these ones. These are clockwise moments. And on the other side, these are anti-clockwise. So that is the order that they chose here. All right. So meaning to say, if you consider that the clockwise is going to be F times the distance back to the what? To the fulcrum, which is the distance. It's what? It's S. So that F, that is going to be F times S. Then in the anti-clockwise, we're going to have Fn going to the fulcrum in that direction. So this will be anti-clockwise, this way, anti-clockwise. Fn to the pivot point, anti-clockwise. So that's Fn times the distance, what? The distance L. They are in the anti-clockwise. So that's the same thing here that we're gonna have as we are to consider. And in our case, the frictional force here, the tangential force that is presented, is not considered because it is in line with what? With the fulcrum. So what happens is that there is no thickness of the shoe that is considered from the pivot. There's no thickness. So it will be just like you're multiplying to zero. So it won't have any effect. That's why you see we never consider that one. We never consider that one. So the same thing you do to this one of the clockwise, right? So what is happening? F to the what? Always you're taking your moments about the fulcrum. So back to the fulcrum. What is happening in terms of the movement? Clockwise. So sum of the clockwise moments equal to the sum of the anti-clockwise moments here. So it's going to be F times the distance back here, which is what? Which is S. So that's F times S. In the anti-clockwise, Fn times what? Times L. Just like what we had here. So this can be used. It's a direct one, as we can see, guys. All right, then we're going to move on for this one. This is it for now. So Fn, like I said, or the R that we had before. Remember, we said normal force using R, so that is the case. And where you see this frictional force, the frictional force, sometimes you see given as what? Coefficient of friction times R, or coefficient of friction times what? Times Fn is going to also depend with your textbook, all right? So for now, it is not applied, as this will be taken direct passing through the what? The fulcrum. You won't consider that one. But you are going to consider it on this case when the line of action now of the tangential force, which is our tangential friction force, passes at a distance c below the fulcrum. So here I'm not just want you to take this for those who want to use this one as it is, all right, because I'm going to change and use the same as what I have here, the L and the S. So the C is representing the thickness. So I'm going to change this one and put it as T, representing the thickness of what? The thickness of the shoe that you're going to have. So that I'm going to use it as T, so that for any other formulas that you're going to have later on, you won't have any confusion. Say, okay, this is A represents this. This is C represents this. Yes, you can use that A, B, C concept. It's not a problem. If you understand it, it's very perfect that you can apply that one. It's very, very, very good that you can use it again. All right, so like I said here, we're going to use what? T as the thickness, T. So that is the shoe thickness, the shoe thickness in what? In meters. So we are now having, when it passes through a distance that's below the fulcrum, this is our pivot point. From that, we are seeing that there is a distance covered to where the line of action of the tangential friction force is going. Just like what we had before, it was straight passing through the what? The fulcrum. But this time, it is found at a distance below. That distance will represent the shoe thickness. All right. So remember, guys, like before we said, from our fulcrum or the pivot point to the force, this is going to be called S. This will be distance S and this will be distance L. So you can use your moments just like before. Here it is the same thing. When it is in the clockwise, we're going to have frictional force that side, but as you can see, it is still at a certain distance below the what? Below the fulcrum. So that's our thickness. All right, and this is our S and this is our L. So just going to change our formulas also where we had those A and B, just gonna use S, A, and what, and T. All right, no problem for, so as we had before, guys, this, the left hand side, always for those formulas that we are seeing here, they were being taken as clockwise. They were clockwise moments, and these were the what, anti-clockwise. So for the clockwise, we are going to have F. It is going in the clockwise back to the what? To the fulcrum. That's the distance what? The distance S covered. All right. Plus the frictional force is going to be taken, but you multiply to the thickness. So it is actually this force times distance. Remember, guys, what is happening here? Force times distance gives us what? The torque. Perpendicular is force times radius, force times distance. So here we are calculating torque, guys. So here, to use the frictional force, you multiply to the thickness now. And the frictional force, how do you tell now to say it is anti-clockwise, it is part of the anti-clockwise moment or what? The friction force, when it is a condition like this one, to say the fulcrum is above, the frictional force tends to be going up. Remember, the fulcrum is above. So the frictional force is tending to go up to where it is going up. So as it is going up, this is the easier way, as you can see, going up to the pivot point, going up. So meaning to say whatever that you're going to have will be clockwise now. Here, this is where we have, it will be tending to go up. Where it is, there was this down. So the pivot is up. So it will be tending like this, going up. So as it is going up there, where it is, the direction now, this will be anti-clockwise. So for this one, the frictional force is going to affect anti-clockwise moments. For this one, it's going to affect clockwise as it is going up. So that is how you take the frictional force. It tends to go up because this is on top. If it was below, then it would tend to go down where the fulcrum is. When the fulcrum is up, it tends to go up where it is. So that's clockwise. So the distance now, it is the thickness. For the frictional force, you take the distance as the thickness. So this is thickness. All right, so that's your clockwise. Anti-clockwise, we only have Fn to the fulcrum, that is the only one, times the distance. What is the distance back there? It's L. So this is what we have for the anti-clockwise. So same here, sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. So what do we have in the clockwise? It is only F to the fulcrum like that. So that's F times the distance S. The rest will be anti-clockwise. Remember this Fn, anti-clockwise Fn times what? Times L. And we talked about the frictional force as it tends to go up. It will be, all right, sorry for that. All right, so as it tends to go up, it's gonna maintain anti-clockwise direction. So that's times the what? The thickness. Always you multiply to the thickness, this one. That's it. So you can use that formula to calculate your unknowns. What is unknown? What is unknown for that particular question? So you must work out as many questions as you can. As many questions as you can. Revision is very, very important. Revision is very, very important. There can be conditions that you work with. You manipulate that information, apply your moments. So this will be best if we work them having what? Having examples from there. So you can also use this one. Yes, this one is when the line of action of the tangential force passes at a distance c, which is, we said, we're going to call it the thickness here like this. So you can also use this one, guys, just like before. This will be your S, this is your L, this is your S, your L, like that. So I want you to use that, formulate your formulas. These are the formulas that you're going to have. Just use L, S, T. If you want to maintain them like that. All right. So I'm going to explain these ones much with examples so that it will be easier. It'll be easier that way actually to work with examples. All right. Anyways, further other formulas remains the same. What, like for other formulas that we had before? Does it remain or remains? Grammar is for English people, guys. All right. For those who are doing English language, engineering and English, I don't know. It's like six and what? 6 and 7 does not match. So here's other formulas. Remains the same. One, the torque that is transmitted between the block, brake, and what? And drum. So you're gonna consider that one. The torque transmitted. So this time is gonna be referred as what? As between the block brake and what? And drum. As we had before, where there is a frictional force and the radius of the drum, torque can be what? Be calculated. So it's gonna be frictional force times the radius of what? The radius of the drum. So we have got our torque transmitted between the block brake in what? Newton meters. So that's it. Frictional force. The radius of what? Radius of drum in meters. The frictional force, like I said, maybe you do not have this. You are to calculate it. Remember, I mentioned about this one before. Frictional force from the coefficient of friction times what? The normal force, Fn, or coefficient of friction times R. So it depends. It depends actually with the presentation that you want to have. So meaning to say, in place of the normal force, if the, let's say we have got the frictional force and we need the normal force, we can have it. Divide by what? The coefficient of friction. You can have it. So it is or can be in your hands. From here, the torque can be written as the coefficient, the frictional force is the coefficient of friction times what? Times the normal force. times the radius. So this is another formula again. If I am given the normal force, I can simply use direct formula like that. Here we had a formula manipulated for the normal force in this manner. Why can't we even manipulate it here? Divide by what? By dividing by the coefficient of friction and our radius to the torque. So it's going to be T for the torque over what? The coefficient of friction times the radius, like this. We are remaining with Fn, the normal force. So this represents the normal force from the coefficient of from the frictional force from the torque. You play around with the information that you're given. Which one is easier? So we have the torque that is taken from the frictional force as we consider our block brake and what and the drum. Then the rest of those formulas, guys, for torque, as we had, as long you've got force and what, as long you've got force and the distance that is being taken, like what we had before, from those, from this calculation, like I was saying here, these force terms, there is torque that we are talking about. Here, this force terms distance. The given force here times the distance back to the fulcrum there. It is the torque transmitted due to applied force. That one. Torque transmitted due to applied force. It's the torque that we have there. Transmitted due to applied force. So I want you to use the same concept for this one. Because we have force times distance. What is it? The torque that is transmitted due to what? Normal reaction force. From our normal force or normal reaction force here. This is the torque transmitted due to the normal reaction force. We also have force times what? The distance, the thickness there is the distance that we have. What is it that we're talking about there? The torque that is transmitted due to the resultant frictional force. This one. Where T is the what? The shoe thickness. It is also torque, just like what we had transmitted due to applied force. This one due to the normal reaction, our normal force. This one due to what? Our frictional force. So you can play around when it comes to formulas, guys. So I'm not going to write those ones here, play this and that. All right, let's move on to another basic formula that you're also going to be using now and again, which is the power transmitted by brake. Power transmitted by what? By brake. So that's our P. As the power transmitted, we are going to have this one as 2 pi nt over 60 as before. Speed in revs per minute, that's why we've got a 60 there. So guys, as for this one, there's nothing that is new. The T is the torque as before in Newton meters. So we had this one, just have a revision. So just have your revision. This one, your speed in revs per minute. The torque is supposed to be what? In Newton meters. Another part maybe that I can just add is on the time it takes, the drum to break. All right, yeah, let's consider that one. The time it takes the drum to what? To break. You must also consider this one as part of your formulas. So time is given as what? T. So our time T is equal to, we're going to have, since it is breaking, so we use the kinetic energy as break for break. So it's EK break over what? The work done per second. Work done per what? Per second. Remember your calculations as before. These ones, we had this before. EK break. Remember that's a half or 0.5 I omega squared. So we've got the moment of inertia, we've got omega. All right. Moment of inertia. Then we have got our omega there representing our angular velocity. Then we have got the work done per second, which is equivalent to, when you have got the torque and the mean angular velocity. The mean angular velocity. You can have work done per what? Work done per second. So if we take this and put it together now, you end up with T is equal to, remember the half, the 2 is going to be in the, since it's EK, so it's going to be 1 over 2. So the 2 is going to be in the denominator, all right? So that's going to be IW omega squared. This is 2 for this half times this one. 2 times T times omega mean. The mean, we need the mean value there. So you can have your time in what? In seconds. If you play around with these formulas, guys, everything will be just direct. Take note, we say this is what? This is 2. All right, another one. Let me just add, okay, number of revs, but guys, no problem. No problem. Let's just finish with this one. Number of revolutions. So that next time if we were to do questions, I'm not gonna be doing these ones again. Or number of what? Number of tens. Number of tens. So number of revolutions or number of tens can be obtained when we can find the revolutions in actual sense, to say theta representing, to say, all right, pi is equal to this 2 pi. When we consider a complete revolution, that's 2 pi radians, 360 degrees. So from that theta, you can have the number of what? Revolutions. So theta, which is our angle now in radians, can be obtained from the mean angular velocity times time, times the time. So from there, you can obtain the number of revolutions by taking, to say, if we are to convert to degrees, a single revolution is equal to 360 degrees. If you are to work with the radians as it is, a single one revolution is equal to what? 2 pi radians. So you can make or have a conversion from there to say, all right, since I have my theta, you have it in radians, you have whatever that you have, you check, is it going to be more? Is it going to be less? If it is more, then it means whatever that you have here over 2 pi times 1. You play around with that one because you already have a conversion. So whenever you want to calculate those, this one is not number, no. Those are the revolutions that we have to say. We have covered 360 degrees, but how many revolutions do we have in 360? It's 1. So if it is 720, how many? So the angle is not the number of revolutions. The angle is not. But from the angle, you can determine the number of revolutions by knowing this. So it is very, very important that you know that part. Very, very important. And like I said, others, guys, we're going to see later on. Later on, if we check those talk that we're talking about here, Fn, Fs times this, Fn times this one that we have been referring to, they are also maximum breaking torques. Maximum breaking torque. All right. So that's, I'm not going to explain much. And angular acceleration from torque. Remember, torque can be calculated, guys, as what? So many formulas. If you have moment of inertia and angular acceleration, so therefore angular acceleration is going to be torque over what? Moment of inertia. So angular acceleration is in rad per watt square second. Yes, they can go there to those angular acceleration. They can extend questions to that. For this one, revise with other formulas that you had before. Yes, just combine and combine. We are going to look into questions in our next class, applying this information, our moments to solve problems where it is needed, where it is to be applied. Does not mean always that is to be your questions. But in most cases, you will be given these questions with diagrams, so apply it according to that. So let's do revise as many questions as we can.